To quickly review this last page, what we've done is we formed a very special equation. We let A act on the eigenvalue that is the lowest so that we get a lowering operator so that we get 0. Thus y times A times nu will give 0, and we can rewrite A in this form here, re-express it this way so that we end up with a differential equation of this form here. By changing our variables, we notice that this is the inverse of this. So by changing y to another y, we immediately get the equation in the form partial with respect to y plus y of this function is equal to 0. And this works, of course, only when nu is equal to 0. The solution of that equation for the lowest nu, the projection, in other words, of nu equal to 0 onto the position eigenspace is 1 over the 4th root of pi, that's just the normalization for a Gaussian, e to the minus y squared over 2, where y is that new variable. Well, that tells us that this lowest eigenvalue, the one that corresponds with eigenvalue 0, looks, when we project it into position eigenspace, as a Gaussian. This tells us a lot, but what about all of these other functions? Are they also Gaussians or something more complex? Well, they are something more complex, as it turns out, and that's what we need to derive here. We now want to take this next eigenvalue, which is 1, which is A dagger times the lowest one, 0. And we're going to project, we're going to write n, therefore, as 1 over the square root of n factorial, that's our normalization, A dagger to the nth times 0. Now we want to find out what y is, the projection of this nth eigenvalue in the position representation. It's obviously, therefore, 1 over the square root of n factorial, y, A dagger to the nth 0. And we can rewrite that as 1 over the square root of n factorial, 1 over the square root of 2 to the nth power. That's because we have n of these, q minus ip to the nth power, times the vector 0, or we have the vector y. It's not very clear. That's a y right there, times n is 1 over the square root of n factorial, that comes from here, square root of 2 to the nth. There's the square root of 2. It's already under the square root now to the nth power. And we have this factor of the square root of pi that comes from that original normalization, times q, and remember the p becomes d by dq, times I, times a plus I, which leaves us with a minus d by dq to the nth power, e to the minus q squared over 2. That's where that square root of, that 4th root of pi comes from, was from this Gaussian from the last page. Well, this is kind of a complicated expression because outside of this normalization, which is trivial, here we have position minus a derivative, quantity taken to the nth power, acting upon a Gaussian. So this is a whole set of polynomials and derivatives of a Gaussian, all laid out in a way that's not too clear right here. There is a way to get back to normal functions that we're more familiar with, and we do that with the following identity. It's easy to show that q minus d by dq is equal to minus e to the q squared over 2, d by dq, e to the minus q squared over 2. Now, what's the special form for this? Well, you can see that if I take the derivative here, I will get exactly this expression right here. And this term here will exactly cancel this term here, because I have an e to the plus q squared over 2, e to the minus q squared over 2. So it's trivial to verify that, to take that derivative and verify that that's correct. But now the nice thing about this is when I take this to higher powers, when I take this to the power n, each one of these e to the minus q squared over 2 hits another e to the plus q squared over 2 and exactly cancels it. So I'm only left with the one at the far left and the one at the far right. And in the middle I end up with the nth derivative with respect to qn. I do have a minus sign with each term. It gives me a minus 1 to the nth power. So, all in all, if I take all of these and multiply it by my original function, e to the minus q over 2 squared, then one is able to show that this long function right here is e to the minus q squared over 2 divided by the square root of pi n factorial 2 to the nth times the nth Hermite polynomial. And q here is of the form m omega over h bar square root times the small q. So all we have to do is substitute in for this capital Q, and we get the small q back again, which is the regular q in our position space. Now this is really quite incredible, because what we see here is that when we work out the first few of these, is that h naught is just simply equal to 1. h1 is equal to 2z. h2 is equal to 4z squared minus 2. We can see that these are polynomials in every other one in even powers, every other one in odd powers, picking up the odd powers there, so these are even and odd functions. And apart from the listed factors, the incredible thing is that these are the directional cosines between the energy diagonal basis, in other words, the Cartan subalgebra where h is diagonal, and the position diagonal basis. Now we want to look at the harmonic oscillator generating function. To see that, we recall from the equation that we just wrote down that q onto the n basis is this factor times e to the minus q squared over 2 times the Hermite polynomial, the nth Hermite polynomial of q, where un of q is simply the projection of n onto the position representation. Again, remember that this q differs by a small factor between what we think of as the normal position. So this is a kind of a normalized position. What we seek is a generating function, an f of t in q. And the generating function is to be such that this function right here is the sum from n equals 0 to infinity of all the coefficients cn times un of q t to the nth, where cn are some type of normalization constants. In other words, where this function right here is an expansion of all of the different Hermite polynomials as coefficients multiplying the powers of t in a kind of a similar way to the way the exponential expansion is done. Now we recall that un of q is equal to q, and then our un comes from 1 over the square root of n factorial a dagger to the nth power acting upon the lowest state, 0. Now, it follows from that we can define fn to be a coefficient cn times divided by the square root of n factorial a dagger times t to the nth power, acting upon 0. And we're going to choose cn as 1 over the square root of n factorial. After we do that, it's obvious that our function f of t and q is q e to the t a dagger times 0. Because then what we have done is we have made this 1 over n factorial times this term right here to the nth power, and that this is exactly the expression for the expansion of an exponential. So if we write out e to the t times a dagger, we would get 1 plus ta dagger plus 1 over 2 factorial t squared a dagger squared and so forth to give us exactly that expression. Now there's a very important lesson to be learned here, that if we want to find the generating function associated with some Lie algebra, then in fact we can find that by exponentiating the raising or the lowering operator, in this particular case the raising operator. This exponentiation of the raising operator will give us all of the different functions in an expansion automatically. Now, after extensive calculations, we can actually derive what this is in a closed form. We can take the summation from n equals 0 to infinity of un of q t to the nth summed 1 over the square root of n factorial, which was the other expression for this raising operator to the nth power. We've only multiplied it by t here. And we can see, therefore, by now turning that around and looking at this expression, that this is 1 over the square of the 4th root of pi, that comes from that lowest order equation, times the expression of a dagger in terms of the q's and the t's. Again, the very important lesson here to be learned is that the generating function can be obtained by using the group transformation generated by the raising operator e to the plus or minus in the Lie algebra, and thus expressing the result in an alternative basis. Let us look now at the Lie group that is generated by the harmonic oscillator Lie algebra. Now, this Lie group is generated by the action of the operators x, p, I, n, where n is the number operator, Lie algebra, and that's essentially the same as the Heisenberg Lie algebra, with one very important difference. We had in the Heisenberg Lie algebra just x, p, and 1. But what we have done now is we have added this new operator n to that algebra and closed it for a larger algebra. It, of course, contains the Heisenberg, the harmonic oscillator algebra contains the Heisenberg algebra as a subalgebra, kind of as, you might say, a kinematic system. But until we did the Heisenberg algebra, there was really, when we did the Heisenberg algebra, there was no dynamical theory. We could imagine that we had just a free particle, but other than that, there was no other dynamics. Here we actually have invoked a dynamics with this xpin Lie algebra with a Hamiltonian operator that corresponds to the energy of the particle. Script h is h times h bar omega, where h is equal to n plus a half. That's equal to 1/2 p squared plus q squared, where qp is equal to I. And then this, as a whole, forms this harmonic oscillator Lie group. So the new group operator that we might imagine now that we didn't have before is the group operator u of t, which is e to the I over h bar t times h. In other words, we now have a new object, script h, that can be used to generate transformations, and we choose that generator to be e to the I over h bar some parameter t times h, and we can then form an operator z of t out of any other operator, which is e to the I over h bar th z of 0 e to the minus I over h bar t times h. Now, why would we do that? Well, that makes an operator z of t dependent upon this parameter. The operator h, the Hamiltonian, gives us a one parameter group transformation that takes us from any t, any time, to any new time in the future. So it gives us a continuous evolution into the future times, just as the position operator translated us among different momenta, and the momenta operator translates us among different positions. We now have what we would call a time translation operator, which is our Hamiltonian. And this was a definition. Of course, this transformation is well defined in the harmonic oscillator Lie group, but the dynamics of the harmonic oscillator is really when we assume that t is has the interpretation of the time. Now, if we take the time to be extremely small compared to 1, in other words infinitesimal, then we can ignore higher order t squared in higher order. And z of t would be 1 plus I over h bar th. With our operator z, which could be any function of any of the operators in the algebra, 1 minus I over h bar th. Now, this will give us 4 terms. It'll give us certainly our z naught term. It will give us a I over h bar t times, which is right here, hz minus zh, which is the commutator of h and z. Then there's one final term, which is of the order of t squared. But remember, t is taken to be an infinitesimal, therefore this is negligible as a higher order term. Now it follows from this that since z of t is equal to z naught plus this commutator, that we can bring the z naught to the left-hand side of the equation and divide through by t. Well, this is the change in z infinitesimally divided by the change in the time, the parameter on which it depends. So it is dz dt. It is the time rate of change of the operator z. And we can see that it's equal to, over here on the right, a minus I over h bar, and we have interchanged z and h here to give us a negative sign, minus I over h bar t bracket of z with h. Likewise, we could multiply this operator here through with an I h bar and get the following result, that I h bar d by dt of an operator z is the bracket. We had taken this t out here because it's infinitesimal, so we divided it through when it was dt from right there. So we end up with I h bar, I times a minus I is a 1, h bar times divided by h bar will give us a 1 here also. So we're left with I h bar d by dt of z is the bracket of z with h. Now for a state vector, we can look at what is sometimes called the Schrödinger representation. And this is where the vectors change with time. And a vector will change with time because it's been evolved with an e to the I over h bar t times h times the initial vector. In other words, there are two ways that one can proceed. On the one hand, one can take all of the vectors, the state vectors that one has, psi, that represent the state of the system, and let those evolve forward by multiplying by this operator e to the I over h bar t times h, which gives us the group translation in time associated with this operator. Likewise, we can choose another whole representation for our dynamics and let all of the operators change with time. And if we do that, you might say we kind of implode all of the operators for the time development away from the vectors and back onto the operators. That gives us something right here is called the Heisenberg representation, where the operators carry the time development according to this equation, this differential equation, or according to this equation right here. So let's reflect on some of the things we've learned from these two groups. We began with the Lie algebra for the Heisenberg Lie algebra, which consisted only of three elements, x, p, and I. And we found all of its representations. Its eigenvalue spectrum was continuous. And we found that one could choose either one of two representations in which to look at reality. One of those was the position diagonal representation, and the other was the momentum diagonal representation. The position diagonal representation is the one in which we are raised to normally visualize what's happening around us in terms of space and time. Therefore, it follows that although another one may be convenient for some types of calculation and understanding, we eventually almost always want to project that back into the representation, like from energy or memento or whatever, back into the position diagonal representation so we can visualize things. The next very interesting thing that we did is we took that algebra and we formed a product that basically was the Hamiltonian. And that product, p squared plus q squared, apart from constants, kind of lives exactly halfway in between the position representation and the momentum. Why? Because it's a p squared plus a q squared term. So it contributes equally between the two bases. We then said, let's take this as being the Cartan subalgebra, the number operator or the Hamiltonian, and look at this as find the raising and lowering operators. And when we did that, we found the A daggers and the A's, which correspond to the E's. Now those A daggers and A's gave us the entire eigenvalue spectrum. They gave us the generating function. They allowed us to solve the equation, which was the projection of the energy diagonal or number diagonal states projected back onto the position ones. And we found that those were the Hermite polynomials. In general then, the Hermite polynomials, apart from some constants, are the projections of the energy diagonal representation back onto the position diagonal representation. And so now we have two cases. The first one in between position and momentum, which is the Fourier transform. So we see the Fourier transform as the directional cosines in one type of Lie algebra, and we see the Hermite polynomials as the directional cosines, apart from some multipliers, as those in the harmonic oscillator. So all in all, this procedure that we have now used with a harmonic oscillator to make the algebra larger by adding a new element, by taking products, and then closing that and figuring out what that algebra is, that is a very important process, and one that we're going to now see is incredibly applicable to the concept of angular momentum.